right. Well, good morning, everyone, and thank you for joining us for today's presentation. Today is the last edition of our Be Bold webinar series for this year. If you've missed out on any of the previous presentations, you can find them all at our website at inorganicventures.com. Today's presentation is going to be about analyzing zeolites by IV's founder, Dr. Paul Gaines. Dr. Paul Gaines has nearly 4 decades of spectroscopic experience. After earning his PhD in chemistry at Iowa State University, Paul worked in the laboratories of Exxon Research and Engineering and Union Carbide. Today, Paul serves as the chair of the board of directors at Inorganic Ventures, as well as an accomplished web author of many popular guides and papers for fellow spectroscopists. After today's presentation, we'll have a live Q&A session. So if you have any questions during the presentation, please submit them through the chat function or better, the Q&A box in the Zoom format. Without further ado, we'll go ahead and start the presentation. Thank you all.
This discussion is concerned with the analysis of silicon. More specifically, we'll be talking about the current methodologies that are used in sample preparations for silicon analysis. We'll be concerned with that more so than the actual measurement, because all the measurements are going to be done by ICP optical emission, which we consider to be the best overall method for measuring silicon. Shown here are the 8 most common elements in the Earth's crust. Silicon is the second most common element that's measured routinely by plasma emission spectroscopy. As you can see, these other elements that are in order of abundance, Earth's abundance, you'll find these elements with silicon, with the glue being the oxygen, typically. And so you've got alumina silicates, but iron, calcium, sodium, and mag, and potassium. So if you find a sample that's been contaminated, you think, well, I got silicon in it, you may want to check for these other elements as well. Now, silicon contamination problems are rarely, as I say here, not encountered. And the lower you're going for your silicon, the more difficulty you're going to have. So if you're looking at really trace levels of silicon, it's going to be hard to get a number that's dependable because of the blank silicon could be higher than the actual value that you're looking for are comparable. Now, there are methods, a lot of methods available, but the 2 main reagents involved are HF with other acids, strong acids, or the alkali hydroxide carbonates. And I've really kind of, for this presentation, have reduced things and simplified them to those 2 general techniques for preparing the sample. And we will be interested in looking at the analysis of zeolites because a higher level of precision is needed by researchers in that area. And these researchers are folks that are synthesizing these zeolites and modifying their structures by changing the amount of aluminum that's in there and causing the silicon aluminum ratios to go down. Now, when I was first made aware of this problem of precision, typical values were around, 4 to 5%, which was what, in those days, this is going back into the early mid-70s, that was kind of a typical analysis precision for an element of about 3%. And so if you combine the errors here, 3% for the silicon and the aluminum, the uncertainty overall is the square root of the sum of the squares, or 4.2%, and which is a pretty good cry away from the 1% that the researchers needed. Now, shown here is just a general method. It was a method that I was using many years ago. It involved the use of fusion using a automated Clace fluxer, and again, this goes back into the 70s. And in this particular method, it used lithium metatetraborate flux mixture, and there was some lithium carbonate in there. You could add your flux to a ratio of typically 10 to 1 flux to sample, and air propane flames were used. This was automated. You would weigh your sample into platinum crucibles that contain 5% gold platinum alloy, and it was an automated method. So you run off, you set the thing, it goes, it fuses. It takes a fusate, pours that fusate into a beaker containing 5% nitric. A dissolution takes place, and you come back in, let's say, an hour, and everything's ready to go. The fusion method does not require hydrofluoric acid. It can be automated. It does cover a very broad range of sample types. It's good for samples like, let's say, silicon carbide that are resistant or impossible to do really by an acid attack. And the only thing we can really say is it can be problematic with respect to salting out, but that's not necessarily the case. It depends on dilution of the sample with the flux and the type of introduction system you're using. Now, the other method that we'll be talking about and comparing is acid digestion. Now, there are lots of different acid digestion methods, but what I've shown here is more or less a typical representative acid digestion where you're taking around 1/10 per gram of sample, adding, in this case, this was aqua regia, nitric HCl, doesn't have to be that. You heat with the mixture, cool, add HF. You may have to eat more or not, depending, but then you react the excess HF with boric acid, and you bring to a weight or volume. Now, in the analysis of silicon, we're looking for a precision of 1%, and this is showing us that if we can get a 1% precision on each of the elements, that's fine and good, but the overall combined precision for the silicon-aluminum ratio is 1.4%. And really, the precision needed would be one that was really less than 1%. So the goal here, as I've said, is to get a short-term precision of 0.7%, which would result in the maximum of 1% overall precision. Now, both the fusion and the acid digestion methods can have trouble with salting out, and this is the boric acid itself. It's only soluble to a level of about 7 grams per liter as boron. Sometimes the fusions can get more than that, and then over a period of time, depending upon nebulizer design, you can get a little bit of salting out. This can really cause problems with your stability, drifting, and precision. Now, we were using a concentric glass nebulizer and a cyclonic spray chamber at this time, and that combination did improve the precision somewhat, but it was still around 2%, which was not good. And then on top of it, the system tended to drift. Again, we ascribe this to the salting out effect. Now, shown here is a third approach. It's not really. This is taking a sample and doing the acid digestion. Well, we're adding 1/10 of a gram of sample, a little bit of water, 10 drops, 10 mils, it doesn't really matter. Add HF, or we can add HCl or nitric, and then adjust the pH to 7 to 9 with amine complexing agents and bring to a constant weight or volume. Now, we're going to explain the chemistry of what's now shown here are the reactions that are taking place. We're concerned about the chemistry of HF. It's a weak acid, and we want to shift that equilibrium to the left because it's the HF molecule that reacts with the oxygen and it dissolves the silica, not the fluoride anion. And it will react whether it's a silicon oxygen bond or a aluminum oxygen bond, either of those. But with this approach, if you have like an alkaline earth or a rare earth, you can get precipitation. Now, we have found that there are two reactions occurring, both at the surface of the zeolite. One is the HF molecule acting directly with the surface silicon-oxygen bond, and the second is the HF molecule reacting with the surface, but by way of through a hydronium ion that's there. And we found that this second rate is significantly faster than the first one. And now we're going to show you a video that will illustrate this. Okay, we're going to be looking at the order of addition of reagents. In this example, we're adding about 10 mils of nitric acid to a bottle that contains 0.2 of a gram of a zeolite. I think you can see when you slur it around that it looks cloudy. You can tell that there's something there, but it's just zeolite and concentrated nitric acid. And next we're going to add 10 mils of hydrofluoric acid to that. And I think you can see, I can see from here, the solution is cloudy. It doesn't look like it's in. Can you tell? It has a very plain, cloudy appearance. So this is a zeolite with pre-weighed in the bottle. We added nitric and HF. Plenty of material, 10 mils of each. And that represents the normal procedure for dissolving zeolites. Weigh the zeolite out. Now, here we're going to add 10 mils of water. And you can see a solution that looks about the same as it did when you added 10 mils of the nitric acid a while ago. It's cloudy. But now we're going to add nitric acid next. And we'll give it a chance now that the zeolite has been dispersed. We'll try to protonate the surface, add that hydronium ion to get that reaction that we talked about in the main presentation, that K2. So here comes the HF. Now as HF hits, it becomes clear immediately. That solution is clear. And we're comparing it now to the first one, which is still quite cloudy. Now, the normal method for dissolving zeolites would be to heat the sample for a half hour, and it will go in. It's just slower. Now here we'll do a little bit of a close-up comparison. Comparing the order of additions as you want to do it: water, acid, strong acid, and then HF. Okay, another comparison. Now the video clearly demonstrated that the sample that had water added to it first and allowed for the dispersion of the zeolite and then the addition of a strong acid to hydrate the surface, that was a significantly faster reaction than the one that had the acid being added first but without the dispersion and the water. Now this next slide we'll talk a little bit about the changes in acid composition, but I'm not going to focus on this. I just want to mention that you can alter and change the acid composition considerably to your advantage, depending upon what, in the case of a zeolite, what the composition is. Shown here is some of the change that can be made for samples containing, well, problematic elements like calcium. And you would get normally a calcium fluoride precipitate. But here, for samples containing calcium, we found that adding phosphoric acid would complex the calcium and help in eliminating the reaction of fluoride with calcium. That, along with adding a strong acid to catalyze the reaction and shifted equilibrium in favor of HF. Now, shifted equilibrium in favor of HF minimizes the chance of precipitation because it precipitates with fluoride anion, not the HF molecule. So what we've got is a situation where we want to shift the equilibrium to the HF molecule and also change the chemistry a little bit by adding a complexing agent that will tie up calcium, and this combination affects an elimination of calcium fluoride. In fact, we have developed a method for, among other things, silicon, trace silicon, and calcium carbonate in limestone. Now this goes into it just a little bit more, showing the steps that we've talked about earlier. And there is a stabilizer that brings the pH up to around 7 to 9. And then you bring the sample to weight and volume. You can put this through glass introduction systems, and you can get it on you. It won't hurt you. Now, it helps either the fusion or our regular acid digestion, and that's the stabilizer we talk about by bringing the pH up to 8, rendering the HF non-toxic to your skin, because you get rid of the HF molecule. And so you basically eliminate salting out effects and the drift that occurs when you have an acid solution of boric acid. So here are some of the advantages of taking this approach for acid digestion. And you get effectively no silicon blank. The fusion method itself doesn't use HF. And your fusion will give a broader range of sample types. Now, if you already had the fusion capability, basically we recommend that you hold on to that capability. The Unisolve's next net advantage is a better precision. And many other sample types may require digestion. Now, shown here is just for technical support. We have a good amount of information on our website, and including technical videos, etc. And the only bad question I want to remind you is the one you don't ask. So let's go.
All right. Well, thank you, everyone. Thank you, Paul, for that wonderful presentation. If you guys have any questions, now's the time to please submit them through the chat, either, like I said, the chat box or the Q&A box. So we've got some questions starting to roll in here. I'm going to go ahead and ask the first one. First one coming in from Daniel, and he asks, what volume would you use for the 7 milliliter Aqua Regia method for a 0.1 gram sample?
The zeolites, the sample you're analyzing, let's say it contains 20% silicon, and that's Si, not the anti-O2 silicon. I would at least bring it up to 500 mils. You're going to get your best precision at a little higher signal noise ratios on silicon. You don't go too high. but about 500 to a liter would be pretty typical.
All right. Thank you. This next question comes in from an anonymous attendee. They said, thank you for the presentation. Do you happen to have any advice on how to analyze zeolites via XRD?
I know I personally have had no experience with X-ray diffraction. We have used X-ray fluorescence to look at zeolites, and X-ray fluorescence is an excellent technique. It's very dependent upon the density of the sample, upon the matrix composition. And we got into an analysis of matrix analysis routine. It's called MARS, using scatter radiation to correct for that. You can fuse the sample as well with your flux and press it into a pellet, pour it out as a disc. But the fraction have not done that. And so I guess I'll just leave that one there.
Okay. All right. Well, just a reminder, if you all have any questions, we're coming up on the end of our list. Just a few more left to go. So if you have any questions, feel free to submit them now, but we'll move on to the next one. This one's from Tyler. How do you control the formation of SiF4, which is gaseous, versus H2SiF6, which boils at 110 C-ish?
Yeah. The thing that controls that, and you can try this to validate your method, is run the sample with water present. It causes hydrolysis, and you actually won't form these compounds. You get the volatile forms of silicon when you heat it with concentrated acid. And you may have seen methods that ask you to add your acid, add like sulfuric, something higher boiling, concentrated, heat it down until you get to fumes. If you go to fumes of sulfuric acid, you'll lose silicon, but staying with water and dilute acids like nitric and HF, you won't use it. So it's through just the way it was shown there, the addition of water and not applying any heat or a lot of heat. But if you do, you won't lose your silicon. You can prove that to yourself.
Excellent. All right. The next question, will the slides be available for download? I believe that is true. To Maddie running our background and helping us out here, I'm sure she can post that in the chat, but I believe these slides will be available for download after the presentation is over.
Yep, that's right, Mike. They'll be on the website on our technical videos page.
Perfect. Thank you so much. Our next question that we have is, can I ask about the preference of the glass spray chamber versus a Teflon spray chamber? So it's just a person wanting to go over the differences between those two, probably with the Unisolve method.
Yes. There are excellent HF resistant introduction systems on the market now. Back when I started working with ICP, there weren't. And of course, this is going back close to 50 years ago. The reason I went with glass tin was because of the wetting, and I could get good drainage, and I like the use of the neutralizing solution. When that method was developed, I didn't work on that one for right off the bat. Right now, we use a lot of HF resistant systems here on site, and that are made of Teflon. And it used to be your precision would definitely be higher or be worse with the Teflon. So if you've got a system you're happy with and you're able to get the same kind of precision that you would with a glass system, I wouldn't bother changing it.
Yeah, I can add a little to that. We've seen, like Paul said, we use the HF resistant, the Teflon spray chambers in our lab, and they work out great. Just make sure they usually have some sort of coating that'll wear out over time. So you just want to periodically check that coating if you start to see poor performance that you're not used to. Yeah. All right. Awesome. Well, we'll move on to the next question. So this one comes in from Tristan. My lab is seeing elevated levels of silicon in samples made from the hydrofluoric technique. Blank samples with hydrofluoric contain silicon, and blank samples without HF do not contain silicon. We believe the HF is attacking the glass of the torch during sample analysis. Have you seen this problem, and do you have a suggestion for how to avoid it?
Well, yes. Using HF and looking for silicon, high blanks can be a thing. You can go to the torches that have the London and tips on the injection tube. Then they help, but the Unisolve reagent, that was one of the reasons it was developed. The neutralization of the hydrofluoric acid with an amine, you get a mixture of compounds that will not attack glass. Now, if you added, let's say, sodium hydroxide to your solution that contained the HF, you're going to neutralize the HF, and that fluoride ion will not attack the glass, but excess sodium hydroxide as well is caustic. And dilute sodium hydroxide is a pretty good reagent for dissolving silicates or aluminum silicates. So my recommendation would be just neutralize your acid, your HF, with the Unisolve reagents are made of triethanolamine and triethylene tetraamine. Those are the reagents, and bringing that up to a pH of 8 or 9 will work. Get rid of your blank if that's where the silicon is coming from.
Yeah, we've seen that in the past in our lab. I know before you had mentioned the HF resistant torches, we used to use the T-preps all the time for HF samples with HF, and we were trying to get low values on silicon. We'd see that contamination quite a bit, and we'd use the T-preps for that. Yeah,
the triethylamine is a relatively weak base. It's not a corrosive base. As far as I know, it's a safe chemical to work with, and I love it. It doesn't precipitate out really much of anything. Your periodic table tends to stay in solution when the pH gets up around 8 or 9, and that's not the case with ammonium hydroxide or sodium hydroxide.
Yeah, very cool. All right, we will move on to the next question here. Have you investigated using HBF4 as a masked form of HF to digest zeolites and or silica, as in analytical methods 220? They give a reference here. Looks like the title is Substituting HF for Fluoroboric Acid, an Optimized Digestion Method for Multi-Element Sediment Analysis via ICP Mass Spec. If so, what are your thoughts?
Well, to answer your question, yes. And at one point, and we may still have as a product a high purity of fluorinated boron, HBF.
Mm-hmm.
We offer that to people who weren't allowed to purchase hydrofluoric acid.
Mm-hmm.
And yes, this will work. It works actually just like HF. I believe, as I recall, one fluoride of the 4 stays bound to the boron, and you're not, at least I wasn't able to get it all. The others will come out and react and like you would want them to. My thoughts are, if you're in a situation where you can't purchase HF and your organization allows you to use the HBF4, that's great. Now, I honestly don't remember if I don't know if we have this material as a regular stock product or not.
So I don't believe it's a regular stock product, but we do make it. It's from high purity HF and purified boric acid, I believe. So yeah, it's very, very clean. So if anyone is having issues getting HF into your lab, feel free to reach out to us, and we can probably get you a solution for that in the form of this. So yeah.
We've done that.
Yep. All right. Next question. What fusion mixture would you recommend?
Oh dear. Well, I'll tell you, the one that I reckon, the one that I use, the one that I like is sodium carbonate. It's a higher temperature, but it's simple. I like just being able to put this carbonate in, mix it with the sample, throw it in the muffle furnace at 1,000 degrees Celsius for 15, 20 minutes, and bring it out, cool, dilute acid, and you're off and rolling. You just got to be careful about hydrolyzing out your silicon. Silicon in solution will tend to hydrolyze at concentrations of around 50 to 100 parts per million. So you want to keep that silicon concentration low. By low, I mean 10 ppm is, I think, more of an optimal concentration. So sodium carbonate is the one that I like. Now, the lithium carbonate is also a good one. The only thing I don't like about lithium is that it will attack platinum. And platinum is so nice to work with. I mean, it's stable, it's easy to weigh your sample out. And quite frankly, you're weighing out 100 milligrams of sample in many cases. You want that weighing accuracy to be as good as possible, and the uncertainty on it. And with many containers, it's not as good as I've found problems like with porcelain crucibles. They'll give me fits. But your solid crucibles, the precious metal crucibles, like the platinum, those things are stable. Mike, do you guys tend to use more of the sodium carbonate in the lab still?
Yeah, sodium carbonate seems to be a really good one. And yeah, like you said, with the platinum crucibles, they're so much nicer to work with than, you know, the regular clay crucibles. So yeah, those work out really nice for us.
I think it's safe to say that platinum will add another significant figure. I've used, you know, your porcelain crucibles and your aluminum crucibles, and I would 10 to 1. I would prefer working with platinum and working with weights rather than volumes. You'll improve things by an order of magnitude. On your really factor 10 on your uncertainty.
Yeah. Very good. All right. A couple more questions coming in. We have one from George. Does the Unisolve reagent increase the background and interferences on ICP-OES due to the abundance of organic carbon species? That's a great question.
Well, it is a good question, and I don't remember having looked into that, George. Specifically, it would have to, of course, be at an energy or an emission line intensity that was close to the carbon line. And I don't remember us having any trouble with background volume ever.
I was about to say, I know when we would use it, it would be part of our calibration curve. So we would have preps that were not prepped with that method and preps that were prepped with it. We never saw an issue with backgrounds. So yeah, I would say it's relatively safe. Yeah. All right. We got the last question coming in here from Sam. And he asked, is your fluoroboric acid free of arsenic? This is a great question. So I can sort of speak to this one a little bit. From what I remember of the certificate, I believe it is relatively free, but Sam, I can send you a C of A that has our trace metal analysis. That would have gone through with a full trace metal impurity analysis. I believe it was very, very clean. I don't think there was any arsenic that we detected in it, but I can verify that and send you a C of A.
Yeah. Now, I have had trouble with some HF being having impurities in it. But we make our HBF4 when it comes out really nice.
All right, we got another question coming in here. Does IV sell Unisolve?
Well, do we still sell that as a Unisolve reagent, Mark?
I believe you'll want to search the website for, it's going to be under the UNS product line. I forget exactly what. I believe there's a UNS1, a UNS2. If you search for UNS, you should find it. They are, I believe, stocked, but I can't remember the exact concentrations for each product without looking them up.
Yeah, a phone call, technically a phone call would be in order.
Definitely.
Because each one of those products was designed, geared to handle particular sample type.
Yeah.
The Zeolites was one sample type, and that was the motive, the energy behind getting this method developed. But people are looking at all kinds of sample types. Cold fly ash, it was one that was particularly difficult. And one of our customers used a method we put together for analyzing zeolites that had rare earths on them.
Mhm.
And you wanted to get the zeolite non-heating and quickly dissolve, but not drop out any of the rare earth.
Yeah.
Like, and lanthanum is one of the worst rare earths to work with, and one of the most challenging for me at least.
Yeah.
And so, yeah, I mean, and we're glad to let people know compositions if they want to put these things together themselves. We've done, because we try to buy the reagents that are clean to begin with.
Mhm.
And but yeah, let us know what we can do to help you out there.
Yeah, definitely. And it looks like Maddie posted a link in the webinar chat that everyone should be able to see. Going to UNS1 on our website. But like Paul said, definitely feel free to reach out directly to us. We'll get someone from technical support to walk through your process and recommend the correct product. But yeah, we do have that available. And like I said, I believe it is a stock product. So,
yeah.
All right. So we are out of questions that I am able to see. I just want to thank everyone for your time. Thank you for joining us this morning. Thank you very much, Paul, for sharing your knowledge with us. And like I mentioned at the top, this is the last Be Bold webinar for this year, but we will be back next year with lots of things going on, new webinar series. Keep an eye out for ICP conferences. And also, as we finish out this year, keep an eye on our website for new sample prep guides that'll be coming out hopefully very soon.
Well,
So
actually, I'm working on the silicon now.
Perfect.
And I've been meaning to get that out soon. So
yeah,
that will be coming out before the end of the year.
Perfect. With that, I would just want to thank everyone one last time, and we will see you all as soon as we host another one of these. Thank you all so much.